Good afternoon and welcome to the Invention House webinar series. My name is Paul Langhorst. I'm the Director of Development for Invention House. We specialize in conformal coating robotics, and our goal with this series is to bring PCB assembling experts to the table to discuss important PCB assembling issues and concepts. Our inaugural webinar today is called Conformal Coating Failures and Their Causes and Cures. I'm going to change my slide here. And before we start, just a few housekeeping items. Everyone is in listen-only mode throughout the webinar. This webinar is being recorded and all attendees will receive a link to the recording within 24 hours of it being ended. We welcome your questions. Please use the Q&A tool in the Zoom bar to ask questions, and we'll try to respond to those at the end of Bob's talk. So let's meet Bob. So let's meet our speaker. Our guest speaker today is Bob Willis, who has 35 years of experience in providing training, consultancy covering electronics design, assembling, soldering, conformal coating, process failure causes and cures. Bob was a member of the SMART Technical Committee and SMTA Europe. Bob is a specialist in surface mount technology and lead-free soldering. Bob has presented and trained in multiple countries and has created guidebooks, wall charts, and PCB assembling techniques. Bob resides in England, if I hadn't said that already. In recognition of your time today and interest, all registrants will receive a copy of Bob's conformal coating inspection wall charts and guidebook. We also provide a link to Bob's website, which is on the screen already, to all registrants. Bob, the virtual floor is now yours. Let's go ahead and get started.
Well, thank you very kindly. I'll just swap over and select and share my screen now. Good afternoon or good morning, depending on where you are in the world listening to this presentation. And thank you very much for Invention House for inviting me to give a presentation. Yes, just a little bit more of a background. I've been involved in mechanical engineering all of my working life. I'm a process engineer, a hands-on guy. I know how to build stuff. I don't necessarily know how it works. And I've been doing it all my career. So that's just a little bit about me. You can read about other stuff that I've done if you want to when you receive a copy of the slides. As has already been mentioned, I'm providing a copy of my Defect guide on conformal coating and cleaning. It's about 40 pages. That's free. You can circulate it between other engineers. It's absolutely not a problem. In addition, we've got a set of wall charts, which has got a quality control guide. This is basically explaining what you can do in terms of tests, assessments, measuring thickness and things like that. So that's, just an extra range of material, which hopefully will be of use to you. Now, what I wanted to try and do during this presentation is talk about conformal coating, but more talk about process defects. So if we just first of all talk about why we're using conformal coating, it's generally there to prevent premature failure of a product. It's not necessary for all applications, but it does give that level of protection, particularly in demanding environments. It can improve performance on specific components and or locations on your board. So if you've got RF issues, if you've got insulation resistance issues, so again, in that situation, we're only talking about a minimum amount of coating. It certainly improves the environmental protection. So many products today are moisture sensitive, and because the track and gap distance and the operating voltages increase on many products, improving that performance is key. It's also an alternative to putting something in a box, because if you take a product and put it in a box that theoretically is watertight, we've got an alternative which may be cheaper. And remember, if you put something in a box and change the external temperature, if moisture is still present in the box, you can still get condensation, which then leads to failure. So it's understanding those things. Reduces cost of the product. And that's kind of a strange thing, but you've got to think about the end goal. What is your product? What does it need to meet? And certainly ruggedization is another advantage with certain materials. You can improve in a vibration situation or a drop situation. A coating specifically selected for that reason may well give you an advantage there. One of the things always to remember is never go to conformal coating if you've got a problem. Now that kind of, again, seems strange, but if you've got a corrosion problem, if you've got insulation resistance problems, find out what's causing the problem first. If you just put a coating over the problem, you won't necessarily solve the problem. You may actually make it worse. So conformal coating, based on the IPC definition, is a thin, transparent, polymetric coating. The actual thickness of it depends on the specification, and there are different materials with different hardnesses, different insulation properties, and of course different expansion, contraction properties. So it's understanding the material, particularly from your supplier, to get the right product for your particular environment. I've listed here some of the most popular coating types. Their general type designation, i.e. the terminology which is used to define them within the IPC standard, and a guide or an indication of the material's general thickness that you will see. This is not a specification you have to meet in terms of having certain thicknesses. It's the capability of the materials to provide this type of reliability based on these thicknesses. You have to make that call on what you need for your particular product. Now, in terms of information, there are 3 textbooks out there in the industry. This most definitely is the best one because it's the newest one, and it's written by Manfred Super, who was an employee of a conformal coating material supplier, but it's a really very good technical book. And I had the pleasure of meeting this gentleman in Germany, and he really does know his stuff. So if you're looking for something which is the best and newest reference, then this would be the book to look out for. So every once in a while I do surveys when I'm doing webinars, and basically the main reason for coating your boards. And this is a survey of around 90 people, and they said that 64% is corrosion and dendrite protection. So that's why they were using it. 19% electrical performance, or improvement of electrical performance, and 3% tin whiskers. And we'll mention tin whiskers a little bit later on. What conformal coating do you most likely use? Well, acrylic materials tends to be the most popular, quite versatile materials. And then next in line, you'll find polyurethane as a material, and then finally silicon. Silicons are kind of like a rubbery material which has great shock and drop resistance capability. Parylene 6%, and then epoxy at 9%. So that gives you an idea, but remember, talk to your supplier. What is the best material for your particular application? And what is the most common coating problems? Well, thin coating and bubbles. So thin coating, as in you've not got the material where you need it on a printed circuit board, and bubbles. Now, it's not necessarily going to be a failure because you've got bubbles in the coating. It depends what they are, where they are, and the amount of bubbles you've got. But certainly it is an indication that your process is not in control. And then wetting and non-wetting, there are surfaces on a board, and probably the most common problem of coatings not sticking to your board is poor control of your process. That's your assembly process, not necessarily cleaning, just poor control of your process, because you can conformally coat over no clean materials as long as you verify the compatibility of the materials. But non-wetting of solder mask is a classic. If you don't know what solder mask you've got, if you get multiple board manufacturers, then that can be an issue to you. So what are the coating processes? Well, dip coating has for many, many years been a very popular process in very high volume. It's a simple process. We have a bucket full of conformal coating, depending on what material you're going to be looking for. And certain materials are not appropriate for this type of application. But basically, we lower the board into a bucket full of coating. Now, in this situation, you have to, 9 times out of 10, do a lot of masking. of certain areas of the printed circuit board. This video clip just shows a board slowly lowering in to conformal coating material. And when the board is fully submerged, there'll be a hold to allow any material to penetrate around terminations and components, and also to minimize the possibility of gassing and bubbling being present. And then slowly, after a period of time, you'll slowly draw out. So the insertion speed and the withdrawal speed will be different depending on what you're trying to coat. But that's a very popular process, particularly used in the automotive industry. So when you've finished your cycle time, after you've done your trials to determine what that might be, the board is slowly drawn out, as you saw in the video clip. And depending on the coating material, it will then go through a curing operation, and that will depend the recommendations from the supplier for a particular material. The alternative to that is spray coating. Again, this can be jet coated, spray coated. So there's slightly different styles of coating, but what we're doing is either coating the whole of the board, or we're selectively coating selective positions on that board. Now, remember that if you're buying a coating system of this type, somebody's got to program it, somebody's got to maintain it, somebody's got to look after it. So bear in mind that there is some engineering time that has to go into any machine that you've got to set up and program to get the best out of the process. And in this particular case, if you were doing a double-sided assembly, as we'll illustrate here, that you'd have to coat both sides. Now, brush coating, manual brush coating, is typically used just for rework and repair. It can be used for small volume as well. But if you've removed coating to do a repair, which I highly recommend you do, rather than trying to solder through it, which is poor practice, then you may have to reintroduce that coating. And that can be done, again, with the recommendation of your material manufacturer to find the most compatible material. Sometimes you don't actually use the same material. You might actually use a slightly different material or a slightly different viscosity of material. That's basically the runniness of the material in simple terms. Spray coating can also be done manually, as you see in this particular example, and you can see that the operator is using a cake stand, a rotating cake stand, and it's all covered with tin foil because it can be easily changed and cleaned up after a number of boards have been processed. You'll also notice that he's rotating the board, and the idea is to get as even a coating as possible. That's the key thing, and through experience, that can be done. Another alternative, and you'll hear a little bit more about this later on, is again brush coating, but mechanized or robotic coating. Again, you're programming a machine to go through a certain pass to make sure you're coating those areas in a repeatable way. And sometimes this can be beneficial in terms of its coverage and its penetration around terminations. The spray coating tends to spray onto things. It doesn't necessarily encapsulate those things, whereas dip coating encapsulates pretty much everything, unless, of course, you've masked it because you don't want the coating in that particular position. So in terms of inspection, there is criteria in the IPC standards. IPC 610 has a coating reference. There is a NASA conformal coating standard as well, which is nice because it's free. You can download it from the NASA website. And these are just typical examples of perfectly satisfactory coating. And what I tend to do when I'm training staff, I like to get staff and companies to have their own internal standards because it's a good reference. And people like to see their own product. You know, if there's a particular tricky area to coat or get good coverage, you've got a reference for you rather than just looking at a standard which is generic. So sometimes it's worthwhile actually doing that. Now, I mentioned tin whiskers, and really the growth of conformal coating has significantly increased because of the issue of tin whiskers. For those of you who are not familiar, it's a problem that was highlighted with tin finish. When the industry went to tin finish on component terminations, on PCB substrates, and also on RF shields and things like that. The plating process, if not properly defined and controlled, you could actually create tin whiskers. So what's a tin whisker? Well, first of all, this photograph taken from one of our NPL reports, National Physics Laboratory, and from my defect database, which is online at NPL, you see there is coating or lack of coating on the sides of components. There'll also be lack of coating on the back of these SO gull wing terminations. And if you can't quite see it, but there's the short, there's the tin whisker. And this is an individual strand of tin which has been forced out from the tin plating because of stress within the tin plating and causing either a short or an intermittent short. And if you look at this SEM image, scanning electron microscope image, you can see that that lighter gray surface close to where the whisker is making contact, there's no coating there. So again, it's not necessarily on the surface. You've got to be looking around the whole of the lead to see that we've got some form of coverage. And it depends obviously on the application you want. But tin whiskers certainly created lots of industry issues, and coating is one of the things that reduce that. The interesting thing about tin whiskers can actually punch holes through coatings. And the only one it doesn't generally poke holes through is silicone coatings. So again, just a little bit of side information for you. So when you decide you're going to conformally coat and you've justified it, you've looked at your process, you've looked at compatibility of materials, fluxes, soldering applications, cleaning, possibly, if that's the way you want to do it, you've got to define where you want a coating, where you definitely don't want a coating, and where it doesn't matter. Now, I have those three things because a lot of people say where I want the coating and where I don't want the coating, and don't actually say where I don't. It doesn't matter, because inevitably, particularly if you're working with the supplier, if for some reason there's some overspray or a small amount of coating in another area, does it matter? If it doesn't matter, then there's no point in reworking. It's totally unnecessary. So if we look at no-go areas, generally it's the edges of boards, because those boards might be sitting on something, or they might be going in card runners. There'll be mechanical devices that you have to turn or trim that you don't want a coating. The areas that you do want a coating possibly are devices which are susceptible, possibly because they're pitch, very small pitch, or susceptible to airborne contamination and have to be coated. And those areas that it doesn't matter. So those are three things to remember: where it matters, where it doesn't matter, and also where it's crucial. So again, just specify and make sure everybody's aware of where those coatings need to be. So a few problems, first of all. Let's sort of get into some problems. Copper dendrites, sort of most common failure that we see on boards coming from moist environments. And this is a little Christmas tree, which I'll show you in a moment, growing between two surfaces. And a copper dendrite, or a dendrite generally, is a conductive path growing from one surface to another, or one termination for another, because of the voltage, moisture, and contamination. And if you've got those three things, potentially you can have a failure or an intermittent circuit. We can have white residues. Now, white residues are a function, generally speaking, of incompatibility of cleaning materials and the fluxing materials that you're using. And you should evaluate those two things as if you were making a cake. You know, you want those materials to be compatible. If they're not, you get this, and potentially that leads to poor adhesion of a conformal coating if you're going to apply it onto the board, or it can actually cause corrosion products in its own right. It very much depends, and certainly most customers would not accept it. One other area I just wanted to mention is CAF, conductive anodic filaments or filamentation. Now, this is slightly different, and conformal coating won't help you here. It's where you've actually got a low resistance path inside the printed circuit board. When you make a printed circuit board, depending on the materials you use, it is possible that the inner layer and the glass fibers running through the board, between adjacent terminations, there may be a gap. So if you've got any contamination which is present inside the board from the fabrication process, and you've got this voltage applied, this temperature and humidity, potentially you can get a failure. And CAF can be quite dramatic. The product goes bang, or it's an intermittent fault, depending on the severity, the pitch, and the voltage applied. Again, there's more explanation of this a little bit later on. A couple more, three more examples that you might see sometimes. Corrosion or chemical reaction underneath a conformal coating, and that's on the top view here. So what's actually happening here, we've got the dendrites forming, this corrosion product continually forming, and it's actually causing a chemical reaction, a gaseous reaction, which can actually lift the conformal coating. And the unfortunate thing there, if you get into this situation, it gets worse rather than actually better. Verdigris, you may have heard of verdigris that on brass, on copper surfaces. Well, this is just an example on the tracks or pads around a solder joint. Now, typically, this looks nasty, but it doesn't necessarily corrode. It forms its own barrier protection. I wouldn't accept it on a product I was being supplied with or built, but again, it's less likely to be an issue. And finally, right at the bottom of the slide, you've got all of it. You've got the white residues, you've got verdigris, and you've got dendrites. So one other area, hopefully, that conformal coating can assist with is gaseous environments. Now, when you've got a gaseous environment, particularly sulfur, in combination with a silver surface, possibly on a PCB or a termination, it can actually corrode over time. So classic examples of that is products working close to a pulp mill where there's a lot of sulfur in the air. Possibly a product that's working in an environment where there's lots of volcanoes, where there's lots of sulfur. But what you're looking at here, top photograph shows a track has been eaten through by sulfur corrosion. The X-ray image, second one down where I've circled, is partially dissolved tracking based on. And conformal coating can protect products to a degree, but again, it needs to be quite a thick layer. It's best to solve the problem, which is the sulfur in the first place, rather than just putting a coating over it. But this is another one that you might experience. So on to dendrites. This is just a simple example of a dendrite, copper dendrite on a PCB forming. So if you want to do this yourself, it's good fun. It'll impress the kids as well. If you've got two tracks and you've got a voltage between them, and you put a droplet of deionized water on that surface, over a period of time, you'll see a dendrite form. So it's just like a little Christmas tree growing across that surface. And when it makes contact, then obviously current flows and it breaks just like a fuse. And that will continue. So that's where we get an intermittent fault with this type of failure mechanism. Now, this video clip I show on first of all, the video on the left-hand side is a typical example of a dendrite forming in the way I've described. This is the very first dendrite video I ever made back in the sort of very early 80s. I've made color ones, but I only had a black and white camera in those days. And then on the right-hand side, what I'm doing is passing a voltage across a test circuit, which I've created lots of dendrites on. So I'm putting 100 volts across parallel tracks, and what you're seeing is the little Christmas tree lights actually blowing up. So that's what's actually happening. So we've got dendrites present, put a voltage across it. Again, we've got this nice Christmas tree effect. Not something you want, but hopefully that explains when we talk about dendrites. We can also get dendrite formation because of moisture, because of contamination on the surface of components as well. So in this example, this is a simulation of evaluating a fluxing medium to see the likelihood that, after soldering, corrosion could still occur. And you're seeing the same dendrite formation, in this particular case, silver dendrites forming across a chip component. So this can happen on the top and also on the bottom, depending on the fluxes, the situation you're actually in. So that's sort of a common type of failure mode on a component as opposed to a PCB. It's less likely that you'll see it on components, but you do see it from time to time. Now, the final type of conformal coating I wanted to mention is vacuum deposition, better known as parylene. And a parylene is a coating which pretty much 100% covers any exposed area on a PCB. It pretty much has very, very consistent thickness. So if you say you want 5 microns, 10 microns, 15 microns, that's what you get, as long as you've programmed the machine properly. And parylene is the most expensive. It is the Rolls-Royce of conformal coatings. And you can get it with a UV trace, and you'll notice on the right-hand side, we've got a UV light. And the idea of a UV light, as you saw from the inspection photographs, is to illustrate where the coating is or possibly isn't on a printed circuit board. Up until recently, it wasn't available with a trace in it, UV trace in it, but some suppliers will offer this particular service. And people kind of like this because they can check, but it's kind of uncommon for you to get a problem with parylene coating that would warrant it, but it's just a nice to have, and some customers will insist on it. Now, another little test that I do, and my peers have done this in the past, is if you've got a board and you've conformally coated it, how do you check it? Well, you can do very expensive environmental tests, or you can put it in a bucket of water. Now, I'm not being facetious. This is a simple way of getting an idea of what is actually happening. This is a test board of mine. It's an SIR test board, a surface insulation resistance test board, and there are test patterns underneath all these components. So basically, after the soldering and perhaps conformal coating process, I can put a board in a bucket full of water, in deionized water or a saline solution, a salt solution, and I can look to see what's happening. Now, if you look at the first example, the video clip, you just about see some little bubbles there. That proves there is a chemical reaction taking place, and the conformal coating isn't stopping it happening. So the thickness of that coating isn't adequate for this particular test. This is kind of a go, no-go test. It may not relate to any standard you've ever heard, but it's simple and it works. And here's another example. These are on 0402 chip components, and you can see this nice sort of chemical reaction taking place. And I've done tests for conformal coating material suppliers where we've done this test and you don't see anything happening. So if you get the right combination of materials and thicknesses, and you put it in a bucket full of water with power, obviously, you don't get any reaction because all those surfaces are covered. There is an insulating body between all those surfaces. So again, it's just something else that hopefully is of use and assists you. Now, in terms of rework and repair, there is a standard, and IPC cover conformal coating rework and repair within the standard. And it's nicely documented. It's nice, pretty picture books. It's a great training aid as well. I like things that photograph and words so you can tie the two things together and use it for two things. And it shows or talks about each of the different techniques that you can use. I personally believe that it doesn't matter what type of conformal coating you're using, you should remove it to solder through. You shouldn't solder through. Now, people can, they do. But what tends to happen is all of the coating gets all of you over your soldering iron. If you're using a proper vacuum desoldering tool for through-hole components, which you should do today for lead-free technology, not one of these horrible $5 solder suckers you get given away free, you are sucking the conformal coating into the tool. And if your maintenance department or if your operators don't clean the tools regularly, then it's not going to work very well. So just removing that small area to remove that part, because you're going to have to replace the conformal coating anyway. Personally, I think that's the right way of doing it. My personal preference, if we are going to do coating removal, it's a little bit more expensive, but actually using an abrasive technique. And what I'm showing you here, first of all, is a video of me removing conformal coating on some SO packages. So you can see the abrasive material is removing the conformal coating. It's basically like a shot blaster, something you would clean the paint off a house, or you would clean up a rusty surface, etc. But it's used for conformal coating. Now, the reason I show you two little videos just to demonstrate this, first of all, a lot of people consider this particular technique an issue with ESD, static generation. Well, this is just Bob showing you with a static meter on the left-hand side of the video. No move, well, there's a little bit of squiggly movement, but nothing at all really. So it is a fallacy that this actually has a problem. If you set it up correctly, shouldn't be an ESD problem. And as I said, you're just going around, in this particular case, this QFP package, removing the conformal coating before you use the rework technique. If you don't, then it might be difficult to remove the part, and it's just going to be a mess to clear up afterwards. So this is, in my opinion, slightly more expensive technique, but a much better, more professional technique if you're going to do rework and repair. So let's move on to some more defects, and I'd like to pick out on some of these defects. Now, all of these defects are included in the booklet that we're sending you. Some of them are included in the posters, and of course there is a copy of each of these images and an explanation in the slides that, again, Paul will be sending out to you. So let's just pick on some good examples and some not so good examples. So first of all, I'd just like to pick up on wicking and capillary. Now, if we're talking about most components, there's not a problem with conformal coating going underneath the part, provided that you've checked the expansion coefficient, the actual expansion rate of the material you're using. Because if you've got a board assembly and you've got something like a BGA, an area rated package, and you've got a conformal coating which goes underneath it, if you've got a large expansion contraction taking place during the operation of your device, you can deform the solder joints and you can break the solder joints. And I've seen it happen. It is a reality. But all you need to do is check with your supplier the material you're thinking of using and looking at the expansion coefficient of your board material, your solder joints, etc. So that's all you need to do to make sure they're compatible. You may do your own environmental tests, but check the basics first of all, and then that shouldn't be an issue. The other thing I wanted to mention is capillary, and capillary is where a material is drawn between two surfaces, very small surfaces, like the BGA you see in the bottom photograph. But if you look at the middle photograph, you'll notice that I'm again shining a blue light on it, a UV light, and you notice that there seems to be a lighter area around where the leads are. And what has actually happened here is the material is capillaried underneath, but it's drawn a level of thickness, a level of quantity with it. So it's actually reducing the thickness around that particular device. So there's still a conformal coating there, but it's reduced in thickness. That may or may not be an issue, but it's something to be aware of. So again, looking at the control of the process is very, very important. And I thought I'd include here, again, another example of capillary, and just to show you what's actually happening. And what you're looking at here, I'm pointing to the material slowly being drawn underneath the package. So basically, this has been spray coated, but because of the specific gravity of the material or the choice of material, the capillary is drawing it underneath, which may or may not be a problem. But again, it's worth understanding and being aware of that. So what I've tried to do in this short presentation for you is talk about the basic process, materials, the most common problems that we face in manufacture today with conformal coating, and also highlight some of the material which is available to us within the industry. And as I always say, thank you very much. Hopefully you've enjoyed the presentation. Looking forward to loads and loads of questions, which is, in my opinion, the most important thing of any webinar, because we like to solve problems. So if we can point you in the right direction, that's got to be an advantage. Paul.
Okay, thank you, Bob. That was awesome. Very detailed. Some of those videos you've taken are just amazing. I've got the Q&A box open right now. I don't have any questions just yet, but Bob, maybe you can just kind of trigger some questions by asking or telling us what are the most common questions that you typically get?
The most common question I get is bubbles. You know, what causes bubbles within conformal coating? And I have to say that if you think about it, what's in the bubble? Most times it's air. And if you put too thick a coating on, then air has not escaped from wherever you put it over. If you then put another coating on, as some companies will do with spray coating to build up the thickness, that bubble can't escape. And sometimes I haven't shown my bubble creation in this particular webinar. Perhaps we can do that in a future webinar. If you put a thickness on, you've got to make sure the bubbles will escape. You know, that volatile material is escaping, because if you put another coating on the top of that, secondary coating to build up the thickness, you know, you won't get rid of those bubbles. So sometimes it's useful and trivial, I know, but the sprayer board, take the board, don't get your hands too sticky, put it under a microscope and watch what happens. I'm a great believer in, you can have the best machines in the world, but there's nothing like your eyesight and magnification to figure out what's going wrong or what's going right. And in my opinion, and I'm sorry, I'm an old engineer, I do get upset when people just rely on the machines to do the job and then another machine to check the machine has done the job. Look at the real product. That's how you learn about how to solve problems in manufacture. Hopefully that.
We got a couple more questions. This first one's from Josh. He asks, any failure modes that are specific to parylene coating to be concerned about?
It's interesting you say that. I used two different coating methods in my youth when I very first started in electronics. One was parylene, the Rolls-Royce of conformal coating, and one was acrylic with a paintbrush. So you know, the most expensive and the cheapest. And I never experienced personally a problem of any of our products, and they went into space applications, military applications with parylene. Parylene is nice. It's expensive, but it's nice because you get the thickness you dialed up if you want, and it can be compatible with no clean, but it's very rare for people to use it with no clean, and it's guaranteed to give you the coverage where everything's exposed. In fact, it's more of a problem in terms of masking. So if you could mask a particular area you don't want coated with sticky tape, if you like, and if that sticky tape isn't bonding to the surface, that parylene will get underneath there. So you've got to be more concerned about how well you protect the areas you don't want coated with that type of coating. So you know, there's positives and negatives.
Okay, and then from Renee, the question is, do dendrites or whiskers happen with FSP connectors / cables 0.5 millimeter to 1 millimeter pitch?
Well, if we talk about whiskers, first of all, whiskers are related to tin plating. If the tin plating process, the material that's used, the plating that's used is poor, incorrect, you can get whiskers. Doesn't matter if it's an inch apart, 1/1000th of an inch, or a couple of microns apart, you could get a whisker. So if the process and materials are in place correctly, which generally speaking they are today, we don't see whiskers like we used to. You know, it shouldn't be an issue. With regard to dendrites, they can be, you know, any distance, because if you've got 0.10000 of an inch, 10 mils pitch on a PCB between tracks, which is quite large today, you can get dendrite there, no problem. It's all to do with the amount of moisture, the amount of contamination, and the voltage applied to that surface.
Okay, and then we have a question, micro bubbles / foamy texture of coating. Elaborate more on the reliability impact.
It's a good question. I tend to find that you've got potentially more issue. It's just like soldering. You know, if we talk about, you know, voids in solder joint, you know, people get very excited when you've got voids in solder joint. Well, we've had them for years. We never had them before we had X-ray. So if you don't have X-ray, you won't see them. Anyway, that's been, you know, a general comment. But the larger they are, generally speaking, I would say that the less of a problem they are. So I'm not talking about, you know, 50% of the solder joint. If they're sort of 10%, 15% by volume of the solder joint, it's not an issue. If you talk about bubbles between active terminations, so bubbles between terminations where there is no conformal protection, that is a sphere potentially. If you've got moisture, remember that one of the things I didn't mention, you've got to always remember that the majority of conformal coatings are porous. They will allow moisture in, but they allows it to come out as well. So it's not 100% barrier. So if you've got lots of voids between active terminations, it is potentially, I've never created it myself. As you refer to, I'm good at trick videos or videos to explain things. I've never been able to create that situation myself. But in theory, if you have voids between terminations, but if you've got voids in conformal coating in the bulk area, on the surface of the solder mask, on the top of a component, that is just, in my opinion, never going to cause failure.
Okay, great. That's looks like all the questions for now. Now, what I'd like to do is tell you a little bit about what we do here at Invention House. As I mentioned in the beginning, we specialize in conformal coating robotics, and I just want to show you a little bit about what we do here, just to wrap things up. So to connect the dots, so Invention House is a 22-year-old company, and we're based in St. Louis. And in the beginning of our company origins, we manufactured variable frequency drive boards like you see here. We made them for military applications, commercial applications, OEM applications, etc. And we had to coat those boards. And we did it by brush, just like Bob was talking about. We'd use a small brush, and we created a downdraft table using the stands that you might see like in a Home Depot store or a box store, those big channelized racks. And we put a piece of board on top with holes in it, pegboard holes, and then we put a solid, so we'd suck the fumes down, and we would put the boards on there and paint them. And it was very tedious work. And the volume was low, so our product demand was kind of intermittent. So we weren't like we were coating boards all the time, but it was problematic enough to where we were looking for solutions. And my brother Phil, who's the founder and president of the company, and our chief engineer, invented something. So as they say, you know, necessity is the mother of invention. So we came up with a robot to do this work for us. And you can see an image of it here on the right. And it's based on 3D printer type technology with an X, Y, and a Z axis. And so what we did was we started using it internally, and it worked really, really well. And then one of our contract suppliers came in and saw it and said, I'll take one of those. And we thought, oh my gosh, maybe we've got a product here. So we've been pivoting over the last 12 months to launch this product. So it's relatively new, but it's been hard tested within our operation. We have several in the field now. So as Bob said, sometimes, as what we like to say, sometimes a brush is the best solution. And Bob already showed you the different types of spraying that are out there. And the challenge with spraying is that it requires a lot of masking. The spray part goes fast, but the masking part is really slow. Sometimes the masking is tape, sometimes it's caps, sometimes it's material, sticky type material that you put on, and then it semi-hardens, and then you pick it off with the tweezers. So that becomes very tedious. And then, so in our situation, we use continuously fed brush. So connecting down into the brush on the right is a tube of thinner and a tube of the coating material, and they're mixed at the proper proportion based on the coating that we're trying to apply. And then it comes out through the brush. So And we can control that brush to within 0.007 of an inch. And so what we're doing is we are guiding the brush around the board to avoid keep away areas and depositing the coating where needed. And this is a look at the robot in action. Okay, what we're doing is we're replicating what a human might do with a brush in their hand. And this is ideal for low volume situations, boards with a lot of connectors and things like that that need to be coated. And this is not the full coating of this board, it's just a partial coating so that you can see what it does. Oop. And just to give you some specs, the unit is about 24 inches square. The working envelope where the boards are made is about 14 inches square, and you can typically get several boards within that period or within that space. It weighs about 35 pounds, so it can sit on any type of a table. It's fed by 110 AC. You do not need shop air, which a lot of coating machines do, so it's very easy to install and set up. You can hold 2 5-liter cans of coating or thinner in there. We support acrylic, silicone, and 1 part urethanes. The viscosity limit is 8,000 centipoids, how you pronounce that. And like all coating machines, it must be vented. So it either needs to sit under a hood or on a downdraft table. And the boards can either sit in a tray like this. It's just a nylon tray that we water jet cut. We actually have what we call a flex grid, which is a movable tray, but they sit in there. And then you can either pull out individual boards if they're completed, or you can slide in a whole new tray of raw boards and coat them and push them out. And this is how the device is programmed. There's a PC that's attached to the device. We don't sell the PC. The customer usually supplies the PC. And there's a joystick attached to the unit. So the combination of the joystick and the PC is used to create the initial coat path. Usually what you have is the board in the robot, and you're doing some dry coating to get the brush moving around in all the various areas. And then once you do that with the joystick, then you go into the program and use your mouse to drag and drop the points around to further improve or optimize the path. And then the path can consist of lines, linear lines that you see here, arcs, or it can jump, it can move up and over units or up and over components. Question came in, how long does it take to learn how to use the Raphael? We call it Raphael because Raphael was one of the best painters out there. The unit, what we like to say is it takes about 10 boards. So to really learn how to program the unit for a particular job, but it's very easy to use. If you're familiar with XYZ access controls, it's a very easy to use program. Yeah, and then we also provide on-site training. So when we deliver a unit, there's 6 hours of on-site training that we provide, as well as unlimited support here at Invention House through websites, through our webinars, phone calls, email support, things like that.
6 hours to clean that process.
Yeah. All right, so that's it then. So everyone, thank you for attending. We are good to go. Bob, thank you so much. With your, Bob's a consummate diver, so he loves to dive in the Red Sea and other places. And thank you for much for your time, and be safe on all your dives. And thank you everyone for attending. Bye now.